Good morning. I'm Karavanic, a professor at Portland State University, and today I'm going to present our work on workflow critical path. Much of this work was done by my former student, Nguyen, who has since graduated and moved on to employment. First, I'd like to describe the motivation for the project. Today's HPC workloads often integrate what we would have considered big data approaches, such as machine learning, analytics, visualization. And this, in combination with the push to exascale, has led to an increasing focus on data movement, copying, and filtering as a common source of performance bottlenecks. This would include application data and checkpoint data. There's also been, over the past decade or more, development of workflow management systems to manage design, orchestration, and performance across a workflow. An example is Pegasus. But many applications were developed outside of any workflow management system, and they continue to be developed that way. And so these patterns are true from small to large scale. Holistic HPC workflows are workflows not developed with a particular package, and they comprise multiple independent applications, libraries, scripts, or codes. Here we're showing a sketch of what a typical workflow might be. The orange-brown boxes at the bottom show the different stages: staging in the data, pre-processing of the data, an MPI application that might be long-running, some post-processing analysis of the data, and finally, visualization. And what we're showing here is, in the green circles, the different data sets or subsets involved in this entire workflow, where the arrows represent copying or moving of the data. Another motivation for our work came from the Drought HPC project. Drought HPC is a code to predict drought for target geographical area that was developed at Portland State University by hydrologists in the civil engineering department. We worked with them to improve the performance of Drought HPC. And what we found is the key issues related actually to the flow between the different components of the workflow. That is, they had a locally developed Python script, but they were using the Vic hydrological model, which was developed at University of Washington and is a full application rather than a library. So the Python script called Vic within a loop, leading to a lot of time spent actually in the Vic initialization process. There was also a large number of file creation, reads, and writes, because we're passing data between the Python script and Vic as we go through the loop. So our goal became, can we have a more automated solution to discover performance bottlenecks in holistic HPC workflows? How can we characterize the performance over an entire holistic HPC workflow? Our approach is to use web and cloud-based technologies to develop a tool to efficiently calculate workflow critical path. We also developed a set of simulators to test out the approach with common patterns of holistic HPC workflows. There's no time here to go into details on the related work, which is contained in the paper, but I'll just say that workflow critical path and program activity graphs have been used in performance going back at least to 1988, where Miller and Yang posted their paper. And work has continued since then, both in making the critical path more efficient and allowing it to scale up as the scale of our applications and platforms has increased. Hollingsworth back in 1998 figured out how to piggyback the critical path profiling data onto existing MPI messages to reduce the overhead. And more recently in 2017, Nathan Talent and his group developed representative paths, where they reduced the total number of paths through the MPI code to a much smaller subset that should be the concern for performance reasons. Our work is also highly influenced by large-scale distributed tools developed at Google and Facebook that are in production use and handling a very large number of requests and trace information. There are many HPC-specific performance tools, and the most closely related work to ours is Harold et al., who looked at integrating with a resource manager in order to link components of an entire workflow for profiling. Our prototype, called Crux, is a distributed end-to-end tool to calculate workflow critical path analysis. And it includes an API based on REST technology, Crux database, for which we implemented with the Neo4j graph database, and the user interface, for which we use currently the Neo4j user interface. We also developed the Crux toolkit, and so this includes a simulator, some tooling for local deployment, and tooling for cloud deployment using Amazon Web Services. So Crux's novelty relates to the fact that it's a web-based design to solve an HPC-specific problem, that it measures a new metric called workflow critical path, and it's a data-oriented approach. The nodes in Crux are in workflow critical path and Crux represent data state. And so we store information about the size, format, location, and origin of the data. Each edge represents a data mutation, which represents operations made on a data state that result in a change. The Crux architecture shows that each application that participates in the workflow, which may or may not run concurrently, each connect individually to the API server, which in turn connects to the database and the user interface. This allows you to see the critical path in progress at runtime. Here we show a quick sketch of the deployment of Crux in an HPC cluster. We note here that by coloring these boxes green, we're indicating we are pulling some nodes out of the general compute pool in order to use them for Crux. And there can be a varying size as you wish to scale up Crux. There is a use of a load balancer here and to the user level in order to divide the work evenly across the set of nodes. So traditionally, critical path has to compute the longest path through the program activity graph. And critical path algorithms typically use shortest path algorithms that are modified. For example, Dijkstra's single source shortest path code. The Neo4j provides delta stepping, which is a parallel version of single source shortest path. To use this with Crux, we assign a cost to the edges, where each edge is assigned cost as 1 over the difference in the elapsed time recorded for node A and node B. And so this means large time differences will receive a small cost value, which is what we need to compute critical path. For data-oriented graphs, the vertices are not computations, the vertices are data states. At workflow scale, one node can represent an entire code or operation. So this is different from an MPI application version of workflow critical path. Much of the computation is completely omitted from the graph, which does help us with scaling. We only need to keep track of cases where we are changing the data state. And note that the elapsed time here does not imply computation duration, because this cannot be used for profiling because we're including the wait time for I/O. To test and explore workflow critical path, we've implemented the Crux workflow simulator. This includes a simulator manager, which launches and configures and controls a set of particular workflow patterns or simulators. Each simulator is run in a container. And so you can extend, you can create new simulators, and you can specify new patterns or combinations of the simulators to give us a common holistic HPC workflow patterns. So the first experiment we did was just capability and correctness, and make sure that we could correctly determine the workflow critical path on these common patterns. So we tested 5 combinations with the simulator. One we call generic workflow, data splitting, checkpointing, multiple data inputs, and create delete. And so we checked the results by visualizing the full graph and the workflow critical path and confirming the accuracy. All the tests passed, and we did demonstrate that Crux is able to correctly determine the workflow critical path for all of these combinations of patterns. We conducted a number of performance tests on both performance capability and scalability. Here's some key summary. The Crux overhead scales up with the number of API calls. The calls are limited to a small subset of all the calls in the code and are focused on the data. For example, for the drought HPC code, for typical size simulation that generated 312,000 API calls. We are reducing the number of compute nodes available to the applications by pulling some nodes to run Crux within the cluster. The load balancer is important to the performance, and also the scalability of the Crux database may limit the rate at which calls can be handled. So we did not hit into a limit with the Neo4j database with the scale of the simulations that we've run so far. Finally, Crux performance is impacted by the network path from the application clients to the Crux server. So we're developing workflow critical path, and it's a data-oriented critical path metric for holistic HPC workflows. It answers the question, what part of the entire workflow should we focus on to improve the performance? This work is informed by previous work on critical path for MPI codes. We've developed Crux, a prototype for workflow critical path, and our initial results suggest this is a useful and scalable approach. Work continues. In particular, we would like to instrument Crux API calls in full HPC applications. And this really requires or pushes the need for automated instrumentation of codes with the Crux API calls, whereas our initial work presented here was done with manual instrumentation. We're also exploring the use of data size in critical path. And finally, looking at saving and storing the results of each critical path run with the PerfTrack tool. That concludes my talk, and now I'm available for questions.